Well, that concludes the Zoom portion of the day. My name is John Burrows. I'm on the LCAN steering committee, one of the organizers of the summit. And it is my absolute pleasure to introduce our next speaker, Dr. Brian Schumann. Dr. Schumann is a Wyoming Excellence Chair Professor in the Department of Geology and Geophysics at the University of Wyoming. He currently serves as the director for the University of Wyoming National Park Service Research Station at the AMK Ranch in Grand Teton National Park. Dr. Schumann's research focuses on past and future climate changes and their impact on water and ecosystems. He is the co-author of the recent Greater Yellowstone Climate Assessment, as well as numerous research publications covering topics ranging from wildfire to drought. And in case you didn't notice, his research and expertise just got a whole lot more relevant, particularly if you were one of the millions of people this summer planning to visit Yellowstone. As seen here in the Jackson Hole News and Guide, very recent story. So with that, it is absolutely my pleasure to introduce Dr. Brian Schumann.
Thank you, John, and thank you for the invitation to be here. It's wonderful to have a chance to speak with you all about this critical topic that is already impacting our lives. And this was exactly the reason that we worked, a group that I'll tell you more about, worked to create the Greater Yellowstone Climate Assessment, which we published last year. It was to facilitate discussions like this, so that you can think about what's our future hold and what do we need to prepare ourselves for. So just a little background about myself. I've taught at the University of Wyoming since 2007. I study how ancient climate changes have impacted this landscape and other landscapes around the world. I'm interested in topics like water and ecosystem change. But that is all giving me context to think about what's going on now. And it's been my real privilege to be able to work in places like this photo here up in the Wind River Range, looking at some of the specific climate impacts there. So the Greater Yellowstone Climate Assessment, which you can find online, and I've got some copies here of the summary of the report for people who are interested. And there's postcards many of you may have picked up on the way in that are the short summary version. But this is a product, this was kind of a grassroots effort. It was not something that was mandated by any government or any agency, but a group of us started thinking that it would be quite valuable to have more local scientific information about what's changing in this region. And so this became a collaboration between the kind of the core leadership group are the people on the photos here. Steve Hostetler from the U.S. Geologic Survey did a lot of the detailed climate modeling work that I'll show you some results from. Kathy Whitlock, who's up at Montana State University, brought the Montana perspective in. One of my students, PhD student David Liefert, helped bring kind of a Wyoming perspective. Charles Drimmel, who is a key person at the Greater Yellowstone Coalition, he helped bring in community perspectives in a different way. And then Scott Biskey was a fantastic scientific editor who helped us try to make the report accessible and not just written in the language that some of us scientists like to speak in. So our goal here, if I can see if I can advance. Our goal here was to create this common resource for communities and stakeholders all across the region. You can find the entire report online at gyclimate.org. But we intended this report specifically to be the sort of scientific compendium of what's changing, what measurements have been made about the climate, the temperature, the precipitation, the hydrology. And we meant this to be a complement to the local knowledge and the indigenous knowledge that we know is so rich in this region. We really acknowledge and value the perspectives of so many communities that have been here, and it's, particularly on the reservation, the communities here that have long relationships to this landscape going back millennia, that are relationships that have lived through many past climate changes that we can learn quite a bit from. So in our effort here to summarize what's happening with the current climate, it is that kind of quantitative scientific perspective, but we absolutely mean it to be a complement. We hope it can be valuable to all the communities and voices around the region. Oops, I jumped ahead. All right, I'm losing track of my slides here. It's going the wrong. How do I go back? Here we are. Thank you. Okay, so the report really focused on this region. And so here in Lander, right on the sort of southeastern edge of what people have called the Greater Yellowstone ecosystem, or the Greater Yellowstone area. For the purpose of our report, we tried to really take what is information that's often presented kind of at global or national scales or even at state scales and bring it all the way down to this ecosystem, this landscape that matters so much to so many of us. And even within that, we then tried to look at what are the differences across the different major watersheds of this landscape. And so we divided the report. The report is divided up, and it refers to these different watersheds. So if you're interested, you can dig in and see specifically what's happening here sort of in the Wind Bighorn watershed as compared to, say, the Snake or the Green. There are some interesting regional differences depending on which side of the divide you're on, what elevation you're at. So we thought this was quite valuable to dig in and look at. Today I'll show you some of those differences, although it is true that many of the main patterns that are important to us apply broadly, and they do apply, of course, beyond just the Yellowstone region, but to the whole Rocky Mountain region, in fact. Oh, there's a lag, and I'm going to have to learn to live with it. Okay, one of the key other pieces of this, I really appreciated the Greater Yellowstone Coalition working with us on, was that we didn't just, for this report, just collect the scientific data. They also did these fantastic interviews with people across the region to understand what is it that we are all seeing? What are the things we're experiencing? What are the things we're concerned about? And so just to kind of give you a quick summary of that as a sort of motivation for where we're going here, is when we did these interviews with people all across the region and asked, what are you seeing changing today? We already see change, and one of the biggest messages that we received was that water is at the heart of it. And so people are seeing changes in temperature. They're experiencing those greater numbers of 90-degree days. We're seeing the obvious changes in wildfires and smoke. We're seeing shifts in species. We're seeing the impacts of the insect outbreaks on our forests. And these are having impacts on things that we care about, habitat for animals that we care about, impacts on recreational opportunities, impacts on our communities. But the number one thing that everyone kept coming back to was water. And so I'll try to come back to that multiple times. Water turns out to be a very complex part of the story, and I think is probably at the heart of what we can expect to see changing going forward. Okay, thank you. So I'm going to start off with kind of just giving you a general sense of like, what have I learned by working on this process, by working on this report? What are the things I took away? And I have to tell you, I came into this as a climate scientist. I knew quite a bit about how the global climate is changing, how we expect it to change, but I was still stunned to realize some of the things that are happening here on our landscapes and the impacts that are already happening for our resources and to our communities. And so I'd say there's kind of three main takeaways that, if you just want to remember some three basic things, global warming is here. It is happening. We are experiencing, there really isn't room for debate about that anymore. It's impacting our lives. And we see that. Our places are changing. This is not just some abstract idea that scientists talk about. It's something we are all personally experiencing. We know from the last few summers how different it feels to be here than it has in the past. And finally, the biggest takeaway that I think is important for us to think about when we're together in a group trying to discuss this is that we still have important choices before us. We have opportunity to make changes that not only impact the direction of change, the magnitude of the risks that we face, but also how we're going to respond to those. And I think that, to me, is one of the biggest and most sort of hopeful aspects of this, is to realize that we're not totally doomed here. We're going to face change, that's unquestionable, but we have a lot of choice before us as to how to approach that. Okay, so to kind of give you some broader context to this, I'm going to step back here and think about this from my perspective as a geologist who has studied climate change in this region going back thousands of years. And an iconic picture of climate change is thinking about glaciers. And so I actually am going to start with that piece. This is a photo of one of the glaciers up in the Wind River Indian Reservation up near the Continental Divide. And it was my real privilege to be up there doing some work a few years ago. And these are just amazing locations. If you've been up there, you know them. But they, of course, provide really important water supply to us because they are perennial sources of ice and water that is melting and flowing downstream. But we think of glaciers today as being these little things that are tucked up into the mountains, these little nooks and crannies, these little shadowed cirques up there high in the mountains. But of course, you all know that this was once a place that was impacted by a huge ice age, and the glaciers in the past came all the way down to the valleys. So if you go up the valley here, you go up to the Washakie Dam, or go up to Bull Lake, or continue on up all the way up to Du Bois, multiple places along the road, you will come across these glacial moraines where there were 20,000 years ago, glaciers that came all the way down to the valley. And so the entire Wind River Range was covered in glaciers. The entirety of Yellowstone was covered in a giant ice cap. These glaciers covered this landscape and made it fundamentally different from today. So if you just imagine how different it would be if you were driving up north from here and saw various glaciers coming all the way down to the road. We go right by the edges of these glaciers if you drive north from here. And I kind of think of these as like ghost glaciers. Their presence, if you're a geologist, you can see that they are still there, or they've left remains. I kind of think about it like if you go to Rome, you can walk around, or Athens, you can walk around on the ruins of ancient civilizations. Here we can walk around on the ruins of an ancient, cooler climate. Well, why am I bringing this up? The reason is that ice age was only about 5 to 7 degrees cooler than today. So if you think about the global temperature, it only took about 6 degrees of global warming to transform the world from an ice age to the world in which we live in. So we melted away these glaciers all the way up into those cirques up high in the mountains, and moved forests up past what had once been covered by glaciers. And so the toes of those glaciers today are actually out here in the steppe, in the sagebrush. And yet they used to be these seas of ice. So that was only about 6 degrees of Fahrenheit difference. So when we talk about the fact that things today have been changing already by about 2 degrees, we're talking about a pretty large chunk of that magnitude of change. So those, of course, were ancient climate changes, though, that took place very slowly for various natural reasons. And we know that there's lots of natural causes of climate change. We know that volcanic eruptions impact our climate. We know that the amount of dust and haze in the atmosphere impacts our climate. Changes in Earth's orbit or the sun impact our climate. Changes in the ocean, things like El Nino, impact our climate. But those things which were really important and have totally shaped Wyoming's climate history are not the main thing that's driving what's happening today. And we can really look at this from a quantitative perspective. So here's a plot just showing the temperature, the average temperature of the state of Wyoming over the last century or so. And so you can see, oops, I've got to go back. Okay, so up here is from about 1900 up to 2020. The orange line there is the average temperature of the state. And the blue line is we could make an estimate based on all those natural causes of climate change that we know about. How should the temperature of the state have changed? And what you can see there is that it captures some of the ups and downs. It does pretty well. But what it doesn't get, what those factors do not explain, is why we've just had this string for the last 30 plus years of unusually warm years. In the last 30 years or so, most of the years that we might have considered cool are actually pretty close to the average temperature of the state historically. And in fact, since about 1991, we've had almost no truly cold years across the state of Wyoming. And 1991 is actually interesting because that was a function of the big volcanic eruption at Mount Pinatubo in the Philippines. And so for a year, there was all this ash up in the atmosphere that helped shade the Earth and make it cooler. And so if we had not had that volcanic eruption, we would actually have to go back even further, back to the early 80s or 1970s, to get to years that were truly cold. What we've really lost here, what's changed here, is these cold years. They've just disappeared. And what we've started to have are just more and more of the high, really warm years. And so to think about why they're occurring, we have to consider the greenhouse gases. Oops. Darn. Okay. Go back one more, please. Actually, one more before that. Sorry. This one. Okay. All right, so here, we're gonna pause for a second and have a little exercise. If you're willing, stand up with me for a second here. I want you to learn a little bit about why do greenhouse gases trap heat. And so they trap heat because of the structure of these molecules. So imagine that your head is a oxygen and, a carbon atom, and your hands are two oxygens. So that's your C and your O2 out here. And they're attached together by bonds, which are your arms. And so what happens when energy is coming up from the surface of the Earth is it hits those bonds, and sometimes it causes them to bend. So like this. So everybody can do this is a little molecular yoga here. So remember, one of the most important things about CO2 is that it captures heat because it causes the molecule to bend. The other thing that happens with these molecules is that they stretch. The bonds go in and out. They capture other wavelengths of heat that's trying to escape by going out. And in fact, it actually does it two different ways. Sometimes it goes like this. You can do it. And sometimes they go in opposite directions. And if you're a water molecule, now we can change ourselves. We're going to be an oxygen with two hydrogens are our hands. And that's actually kind of a bent molecule. So you want to do it like this. The really important thing about water is as the air starts to get warmer because the CO2 is capturing heat, more and more water vapor gets evaporated into the atmosphere. Well, water vapor also traps heat that's escaping, and what it does is it likes to rotate. So you can spin around. So just remember, there are these really tiny molecular actions that are taking place all in the air around us, and that's what's trapping the heat and preventing it from escaping. And so we understand the physics of that actually really well. We've known about those things since the 1800s. So thank you for indulging my little molecular yoga there. So as we add CO2 more and more to the atmosphere, more and more of those little molecular actions are taking place, and that is what's trapping heat. So if you go to the next slide, we add a black line in here, the next one, where we incorporate the effect of those molecular additions to the atmosphere. That is what seems to really explain why we've had this string of warm years and the absence of cold years. And in fact, we have to invoke that to understand why things have changed. So in many ways, the odd thing about climate change is that it's much more predictable than weather. If I tried to tell you this afternoon where the thunderstorm was going to rain in the valley here, it would be really hard to get that right. But I can absolutely tell you next summer is going to be hotter than next winter, because some of the certain physical aspects of the climate system are pretty specific. And in that same way, we understand that these changes in the composition of the atmosphere are what's driving the temperature change here. Okay. So this also, though, leads to the biggest uncertainty about the future. The biggest uncertainty about the future isn't the physics of the climate system. It is what will our choices be. So if you look at this graph here, it's a graph of the concentration of the amount of CO2 in the atmosphere. So right now, if I took 1 million molecules in front of me here, about 420 of those would be carbon dioxide. If we went back about 150 years ago, only about 280 out of that million would be carbon dioxide. The question now is, how much more are we going to add? And so if you look at this graph, the black line is the amount of CO2 we've added to the atmosphere so far, or how the atmosphere's concentration in carbon dioxide has changed. The various colored lines are different scenarios that people have been using internationally to guide our thinking about the future. And so for the Greater Yellowstone Climate Assessment, we focused on 2 of these to kind of really represent kind of the bounds of outcomes that we might face. One is the blue line there, where you can see CO2 kind of continues to go up over the next few decades, but then we eventually get some mitigation behind us, and it starts to level out. It levels out maybe around 575. So instead of 420 molecules out of 1 million that are CO2, 575 of those are CO2. On the other hand, there's a scenario which is sometimes known by its technical name of RCP 8.5, which is the more extreme scenario where we don't really get this under control. And CO2 emissions, either on our own part or because of feedbacks in the Earth system, continue to rise. And by the end of the century, we get up to almost 1,000 parts per million, 1,000 CO2 molecules out of 1 million in the atmosphere. And those are 2 very different situations, as I'll show you. But what I'll show you as we move forward and look at the projections here for the future, we're going to contrast those 2 scenarios, and I think they help to illustrate the amount of choice that we still have before us in terms of how this plays out. And that's where the greatest uncertainty really is. Okay, so here is some simulation results that illustrate how those 2 different scenarios might play out in the future. So this is temperature, above average, above the 20th century average there on the vertical axis, and time from 1900 out to 2100 across the bottom. And the black line is roughly historically what has happened, and the blue and red lines are different scenarios of simulations. And these encompass dozens of simulations that different groups around the world have done about the global climate. And we've captured their simulations and then done some additional work with those to represent what would that mean for us locally here. And we've averaged all these dozens of simulations to represent those 2 scenarios. One where we have some mitigation of the temperature of the CO2 into the future. And another one, the red, where we really don't get that under control. And if you look at the projection here, there's of course going to be years that are going to be warmer and cooler. Things are going to bump around as it goes up. But gradually, in the blue scenario, where we have some mitigation of the amount of greenhouse gases to the atmosphere, we get up to about 7 degrees of warming above the 20th century by the end of this century. And on the other hand, if we don't really mitigate and we allow the amount of carbon dioxide to continue to really build substantially in the atmosphere over the coming decades, we get up almost above 12 degrees Celsius. Now, remember, I want to put this in perspective again. The last ice age, the end of the last ice age represented about 6 degrees of warming. So melting away all those glaciers that had once covered the winds and Yellowstone, totally transforming this region, that was about 6 degrees. So with some mitigation, we are still talking about an ice age worth of transformation of this landscape. So obviously we're not talking about going back to an ice age, but imagine how much warmer it would be if we made things as warm again as it has warmed since the last ice age. That is the amount of transformation that we are, to some degree, bound to have to live with. The question is, do we want to stop there, or do we want to have twice that amount? And that's where we still have choices. So we both simultaneously face some really significant changes before us, and we have the ability to rein that in a bit so that there's still time to prevent that from being truly catastrophic. Okay, so what we're just... Thank you. Yeah. Thanks, the battery. Yeah. Thank you. All right. So what are some of the changes that have already taken place? So since 1950, the Greater Yellowstone region, if you take all the weather stations around the region and average them, we've warmed by about 2.3 degrees Fahrenheit. So it's been a pretty steady increase in temperature. Of course, there's some years are warmer, some years are colder. You're always rolling the dice as to whether you're getting a warm or cold year, but we've loaded the dice. We're getting those warm years more frequently. This has actually had some other important consequences. So for example, mean snowfall, which on average across the region where the weather stations are located, we receive about 100 inches of snow every winter. But that's actually gone down by about 24 inches. Now, there are some places, certain elevations up high, where there's actually been an increase in snowfall. There are like parts of the Teton Range, for example, where there's almost been a doubling of the amount of snowfall that's occurred. But for the most part, on average, we've lost about 25% of our snow since 1950. And what's interesting about that is that we've not had a reduction in total precipitation. The total amount of precipitation has stayed about the same. It's just that it's warmer, so more of that snow is now falling as rain. Oops. So this also has the consequence of, as things have become warmer, the snow is, of course, melting sooner. And so since 1950, on average, if you look at all the streams where we have measurements of stream flow around the Greater Yellowstone region, snowmelt is happening, the peak runoff is happening about 8 days earlier than it did in the 1950s. So about a week earlier. And these are the trends we expect to see, but they really are pretty clear here. So when I said that the precipitation, though, isn't changing in terms of total amount, that's annually. It turns out if you break this out by month, that you actually do see some pretty important changes. So this graph here, each of the bars represents each of the months and how much precipitation has either increased or decreased since 1950. And you can see that in the winter months and in the summer months, we've actually had reductions in total precipitation. So there's less midwinter snow and less summer rain, but we actually have had an increase in precipitation both in the spring and the fall that essentially cancels out the drying that we see in the winter and the summer. So our shoulder seasons are getting wetter than they've been. This, of course, has consequences as we unfortunately have just experienced. So one of the big oddities here about how water is changing in this region is that we're simultaneously having a greater risk of spring flooding and a greater risk of summer drought. And so these graphs here are by month, just two of the different stations on the Yellowstone River, which, sadly, this is the photo of it just last week. The Yellowstone River is a place that has been changing. So if you compare sort of the mid-20th century to the early 21st century, if you're up at Yellowstone Lake or out at Corwin Springs, where the river gauges are keeping track of what the river is doing, we see significant increases in river flow in April and May, and even into June, but then then exactly the opposite, significant reductions in river flow throughout the whole summer. And this is the pattern that we're seeing across the whole region. Now, of course, it depends on how we're managing the water. If you're on a heavily managed river system, you may not experience this the same way, but this is kind of the natural pattern that's playing out. So what does this all mean for the future? Well, let's look at some of the projections here. So this is just from our simulations showing how that river flow in the Bighorn River, the Wind River, might change going forward here. And so this is by month. And if you look at the black line there, it shows essentially the equivalent of how many inches worth of rain are running off down the river every month. And right now we get our peak runoff, of course, in May through June. But if you look out towards future decades, and the colored lines represent progressive decades forward into the future, we see this pattern that I just showed you continuing to play out. So the spring runoff will shift earlier and earlier into the year. So we get greater flows, higher flows in March and April than we've had. And at the same time, once that river has flushed all that water out of the system, then we expect to have much lower flows from June all the way through to the end of the summer. And so we have really big losses of water at critical times when we need that water at the height of the summer. Another way of looking at what's changing is to think about the experiences that we have on a day-to-day basis. So if we look at, and here I'm showing you a graph that represents what's been changing in Jackson. Think about like how many days per year are below freezing? How many days per year are below 32 degrees Fahrenheit? And today in Jackson, it's almost 250 days out of the year. The average temperature is below freezing, which is quite a lot. For all of us living in Wyoming, that sounds normal, right? But if you look at the projections here for the future, if we have some mitigation, that slowly declines, but then it levels off at maybe about 200 days per year. But if you don't mitigate, you drop down to almost, getting to about 175 days per year below freezing. And that, in some ways, that doesn't necessarily sound bad, but if you think about what that means for our snow, for certain animals and organisms that depend on cold winters to thrive, these are pretty significant changes. But the one to me that really stands out is not looking at the cold part of the year, but actually looking at the summer. So here's Jackson again, but now looking at those numbers of days per year that are above 90. And Jackson today doesn't often experience many days above 90. I mean, Lander is a much warmer place, 25 days on average above 90. But in Jackson, it's very rare to have a 90-degree day. But even with some mitigation of our carbon emissions into the future, we can expect Jackson to start experiencing about 2 weeks per year of 90-degree weather. On the other hand, if we don't get that under control, this is where our choices really come into play. Jackson can become a place that goes from having rarely had 90-degree weather to having 2 months of 90-degree weather. That's a fundamental change to our system here. And you think about that just sounds hot. I don't want to live there. But also, think about what that means for wildfire risk. That's just that many more hot days where you could ignite a big fire. Think about what that means for evaporation out of our reservoirs. That's just that much more loss of water. Many people don't really realize, but our number one use of water in the state, essentially equal to our agricultural use, is evaporation out of our reservoirs. So you add in all these hot days, and that just becomes a bigger problem. So here's the part that really stuck with me the most, and that is the impact on our snowpack. So if you look at these maps up here, the maps are showing the black outline there is the outline of the Greater Yellowstone ecosystem, and the thinner black lines are the watershed boundaries. If you can make out that there's kind of a blue blob in the middle there on the left, that is the region where now almost all of the winter precipitation falls as snow. So it's sort of outlining all the high country. Most of Yellowstone, you can see the winds kind of coming down there on the bottom right. That is the way we think of this region now. All the high country is just buried in snow. I come up here from Laramie up to Lander to go cross-country skiing multiple times during the winter. I know this is a snowy place. But if you look at the projections going forward, we start to lose that snowpack. And even by, say, 2060, 2080, the snowpack is really restricted only to the very, very highest elevations. And that, to me, is the biggest change that we face, and the one that's most startling. That water is our lifeblood. That snow is the lifeblood that is our water. It's critical to so many economic activities. It's critical to our ecosystems. And so to transition away from a place that's dominated by snow to a place that would be much more dominated by rain, even if it doesn't change the amount of water falling out of the sky, just makes this a very, very different place to live. Another way of looking at this is just to look at it in elevation. So this is the same information, but plotted by time across the bottom there, going out towards the end of the century. And the boundary there between red and blue is essentially the rain-snow line. Today, it's about 6,000 feet on average across the Greater Yellowstone region. And as we go out into the future, it climbs and it gets almost up to about 10,000 feet under the scenario where we have some mitigation of our carbon emissions. If we don't mitigate, we go to the next slide, that just continues to creep up, and eventually by the end of the century, the rain-snow boundary is up about 13,000 feet. Just for perspective, the top of the Jackson Hole Ski Resort up in Jackson is about 10,000 feet. So even under the first scenario, there's really significant impacts to, say, economic activities like skiing. So this is, to me, this is one of the things that has really stuck with me in working on this report. I knew the generalities of climate change. I didn't really understand how this would fundamentally change what it means to live in Wyoming, which is such a cold, snowy place, but where that water is not just important to us and our ecosystems, that's the water that goes down the stream to ends up in places like Arizona and Nevada and Utah. Other parts of the region depend on that same snow, and yet we're looking at it really realistically going away. So this is why, again, I'm so glad to be here with all of you. I think the important part here is to now discuss what are we going to do about those choices. We face fundamental challenges to our water supply, to our fire risk, to our health. We need to discuss how do we manage that, how do we live through that, but also how do we make the choices that might make that less intense. This is the type of discussion that really, really is needed. And I so much appreciate all of you being here to be part of that for this reason. So I'll just leave you with the last slide, which is just to remind you that global warming really is here. Things are changing. Our snowpack has declined by about 25% on average already. So our places are changing. But we really do have choices in front of us as to how we face this and how to make it less severe. So thank you very much. I appreciate the chance to talk with you. Yes. All right, so I guess we have time for a few questions.
Thank you, Professor. What caused the end of the Ice Age?
Actually, interestingly, it was a natural increase in CO2 that we don't totally understand. Why did the Ice Age end? It was a natural increase in carbon dioxide. Carbon dioxide during the Ice Age was only about 180 parts per million, and it rose up to about 280, and that 100 part per million increase was enough to cause 6 degrees of global warming that melted the ice sheets. We don't totally understand what naturally caused that, but we know it was part of a set of cycles that repeated over the last million years. We went through repeated cycles of this that seem largely to be driven by changes in Earth's orbit that are a function of just the gravitational pull of other planets on Earth. So it was really truly a natural cycle, and what we've done now is to really deviate from that in a substantial way. In fact, you may sometimes have heard that scientists back in the 70s would say we're headed into a new ice age. Well, that was true, but that was because we understood these cycles. We were just beginning to examine those and realized that over many thousands of years, we would be slowly headed back to a next ice age. But now we understand the amount of CO2 that we've added into the system basically prohibits that from happening.
Thanks a lot for this presentation. I think it's been great. Alarming. Kind of two questions. One real brief. Do you believe that the feedback loops that have already started are adequately included in the projections that you've made?
Yeah, really good question. Like, there are feedback loops in the climate system. There are really important feedback loops in the climate system that could kick into gear and amplify what we're seeing. Many of those, I would say, I do think are well represented in the models. And I say that because we can take these, I did a project a few years ago where we took this same climate model that we're using to make these future projections, but we ran it backwards all the way to the last ice age. We ran 21,000 years backwards in time using the supercomputer down in Cheyenne. And it actually was spot on with the temperature estimates that we were able to make using geological evidence. And so in that sense, I feel like the models there's a lot of reason to have faith in the models, at least in terms of their ability to get temperature right. Are there other things that maybe we're missing? Sure, I wouldn't be surprised if there's still surprises in front of us. But right now, I think we can feel reasonably confident that the models are doing a good job of capturing most of the dynamics. Yeah, that's a really good question. The sum mitigation scenario. So if we were to actually implement all the proposals and pledges that people have put on the table right now, I think we'd be in that sum mitigation category. However, it's unclear whether we're really living up to those pledges. And that is the fundamental challenge, I think. I'm reasonably optimistic we're not going to go into the really extreme scenario. And so we focused the report really on that sum mitigation scenario because there is some sense that we'll get there eventually. But I say that very cautiously because while people are talking about it and making pledges, we're not fully seeing the action yet, and we really need to see that action. And I'll just say there's two parts to that. One is, I respect very much the idea that this is a systematic problem, that it affects our whole economic global system. So any one of us alone, it's not just on us to make our own personal actions. We have to push for the political change, the economic change that will make the system change. That's what's required. At the same time, I do also think that we personally have to take some expectation or like live up to the expectation that we're not going to be able to do every single thing that we could do before. Our personal lives in some ways do have to change. And I'm not going to fly off to Tahiti next week for a vacation. And in fact, I am personally striving not to fly very much at all because I think I really do need to respect the fact that my personal choice does contribute to that systematic change. So I see this as two dimensions. It's not on us, any one of us personally. There's been an effort to sort of move away from political action by making people feel like it's only on them to do it. But I think we have to meet it halfway. So.
Under your two different scenarios, are there predictions about what's going to happen to the flora and fauna?
What are the impacts for our ecosystems? I can tell you, as somebody who studied how ecosystems responded to the change since the last ice age, that 6 degrees of warming would profoundly impact our ecosystems here. I would expect to see some really dramatic changes, as we're beginning to see already. A 12-degree change would be, I think, start to make Wyoming somewhat unrecognizable in terms of what animals and plants would really naturally thrive here. This is still, I think, the bigger part of the uncertainty right now is we can say with some certainty how the climate will change. What the ecosystem impacts will be specifically, I think, is something we really need to work on. And I wanted to mention that with some colleagues, I've been very fortunate to just receive a grant from the National Science Foundation at University of Wyoming. It's a $20 million grant for the next 5 years to launch a project that we're calling WYACT, which is the Wyoming Anticipating the Climate Transition. And our goal is to work with communities and stakeholders around the state to help plan for and think about the future. And one of the big efforts that's going to be involved there will be actually simulating not just the climate impacts, but what will the ecosystem changes be. And so, I expect fully things like forests to move upslope in some ways, of course. We may lose some high elevation types of ecosystems and animals. Fire is inevitably going to be a very big part of our near future, but it's interesting to think out into the future as we burn up all those forests. It's possible that eventually we actually run out of fuel for lots of fires. So how some of those things play out is actually going to be somewhat complex. I'm not holding my breath on that. In fact, we'll be holding our breath, I think, a lot. There's going to be a lot of smoke in our near future, I believe.
Thank you. Andrew Schneider with the Wyoming Arts Alliance. There are about 11,000 folks in the state who make a living relative to arts and culture. In a state with 23 counties, we have over 100 museums. How is this study being engaged by those groups, and what is the role of those groups, maybe in WYACT, but just more generally in the relationship between arts and science?
Yeah, I think this is a great question. Personally, we'd love to do more to get this information out to people, and I would love to work with the creative community across the state to help envision these futures. How do we help people to think about what it looks like? And how do we think about what we need to do to respond to it? I personally I'm often thinking about how do we try to approach this in a very hopeful way. We're going to face change, but we can think about it in some creative ways that may be really useful to help us be resilient as other people have been in the past. So I don't have a really specific answer, but I would love to have more engagement with the arts community, the museums, other ways to share some of this information, and that would be wonderful. Okay, one more.
Is it conceivable that at some point science may develop a way to actually reverse global warming?
Yeah, this is a interesting and challenging question. One of the hard things about reversing global warming, and like you may hear a lot about technologies, the state would love to have carbon capture technologies, for example, that would allow us to continue our really important energy economy here. The challenge is that we get energy from fossil fuels in particular because it's so easy to break apart those molecules and release CO2, and that gives us energy. Reversing that takes energy. You have to put the energy back in the box, basically. So it's quite challenging, but there are some clever ways that we might approach some of this. But the practical reality of whether we can do it is challenging. And I'm also very apprehensive about some of the geoengineering ideas, say, spraying things in the atmosphere that might help reflect sunlight away. I respect the notion that that should still be explored. We should understand what the possibilities are there and what the impacts might be, and that those might be sort of emergency methods that we could employ. The basic problem, though, is every day we're adding more CO2 to the atmosphere, and it is a very energy-intensive and challenging process to get that CO2 back out of the atmosphere. So for the most part, most of the CO2 that we're putting in now will remain in the atmosphere for 1,000 years. Some of it will remain in the atmosphere for 100,000 years. So this is a long-term thing that we're working on, and I can't express enough how I think something that's underappreciated is that we are still increasing the amount of CO2 we're adding to the atmosphere. So every year we're ratcheting up the rate at which we're making the problem harder to solve. So I know that's not a super optimistic outlook. There are technologies, people are trying to work on them, but I think we must prepare ourselves for the fact that at least in the near term, we are going to face change. Okay.
Thank you so much for the presentation and the research. It's really enlightening. You focused on 2 scenarios, but the IPCC and other groups actually focus on others, and we're not even locked into that 4.5 future. Did you do any modeling on RCP 1.9 or 2.6 that really limit temperatures? And I just wanted to emphasize, we still have choices to do that as well.
Yeah, thanks, Greg. That's a really good point. We picked these 2 scenarios just to try to keep the assessment from being overwhelming. We still have the ability to make substantial choices that could be even less of an impact than the some mitigation scenario I was showing you. We didn't analyze those for the report, but if you look at the information globally, you can make some inferences that there really is time still. I mean, as time goes on, it gets harder, but we still do have time to act in ways, potentially where we do bring in new technologies and things. We have to be very open-minded, and we would have to be very aggressive about it. But there is still time where the scenario becomes much less intense than even that some mitigation scenario that I show you. The real question is, what's the political will, and what's the likelihood of acting on that? All right. Well, thank you very much. It's been great to have this conversation with you.